Hello, everybody. This is Dr. Andrew Chrysler with EE4495 at Idaho State University. In this lecture, we will return to the design process, and in this lecture, we will consider the system level design. So you will be looking at the system level design for your senior design project after you've completed the needs assessment and the requirements specification, and you're looking into how to break your project into smaller parts. Okay, so previously, right, we started with this process where we took a customer needing a solution to a problem. We looked at the requirements analysis where we had a iterative loop where we got information from the customer and generated this requirement specification. And at this point, you are probably looking into system design. So looking into a more detailed system level design where you have the requirement specification for the final project, but you want to break down the project into smaller parts and design those, and that's the system design. So the importance of system design is this in this phase, this is where a lot of the novelty and innovation originates. And so in this stage, when you're breaking the project down into smaller parts, this is where you can start to think about how will you actually implement the functions that give you the desired output. Remember, we talked about the needs assessment and generating the requirement specification, saying that those requirement specifications should be abstract, meaning they should say what should be done, but not how it should be done. At this point in your project, you should be thinking about how will it be done? What components can you use? Should you be using the digital domain or the analog domain? These types of questions. And this is where a lot of creativity can go into the problem. This phase of the problem is often overlooked by the junior engineer, but that may just be because the junior engineer is assigned the tasks once these functions have already been defined. And so this might be these higher level tasks are ones that you might work on possibly later in your career. So the system level design outcomes should give you some idea of whether or not the problem is tractable. So are there some aspects of the problem at this point that you figure out you cannot actually quantify or measure? And also you should determine things like the actual performance limits of the design. So when you're trying to meet the requirement specifications, how much further can you go beyond those specifications? How much margin do you have? These types of questions are ones that you will be asking yourself. You will also get an even better idea of the costs during this stage in the project, right? Because at this point, you will be selecting maybe chipsets, different components, vendors, suppliers that might do various subsystem elements. So this is a point where you will get even better ideas of the cost. You also have the opportunity at this point to reduce the risk of having a non-functional design in your system, right? And this is because during this task, you will be able to break your final project into blocks, determine what would go into each block, and be able to better determine that each one of those blocks, those smaller aspects, are going to work. So systems engineering, right? This is an entire field or domain that you can get a graduate degree in this topic, but basically it's just a way of taking very complex problems and breaking them down into smaller and smaller, more manageable problems. So this method, right? This is a method and a process that you would use in order to come up with a problem that's so small that it's very easy to conceive the solution to that problem. Right. So at the very beginning, you have a full block diagram trying to determine, for example, how the pump might work. But the further down you break it up, right, you should be able to eventually break it down into just individual subcomponents, perhaps even including just, basic circuits or voltage dividers that do just one single task. And so that's kind of the idea behind systems engineering, is breaking things down into that. So in systems engineering, often you will use one of these block diagrams. And so this is an activity where you build the entire entity. So you want to make a pump, you determine every single subsystem that would go into that pump, determine how that subsystem will act. And so the block diagram lets a reader understand exactly how each one of those subsystems work together in order to make the final overall system. So the block diagrams communicate the structure of the design solution from a system perspective. Each block diagram is going to have a label that identifies what it does. It should have a description of the function. And then the description should also contain specifications. So for that single block, inputs, outputs, ranges, timing, frequency, voltages, currents, all these types of things. These can, if you should be able to break down your system into these simple subcomponents in which not only does the system have a full requirement specification, but each subcomponent can have its own requirement specification. So the connections between those blocks are going to indicate how the entire system has worked and how it's connected and what direction the information or signals might flow through the system. So the block diagram too, it may evolve as your system design progresses, and this is perfectly normal. The first version, which is the one you would do first, right? This is going to be more of a rough sketch with initial ideas. But by the time you finish this project, right, it should be very thorough, right? You should be able to have every block totally specified. So as you go along, you will want to continue to refine this block diagram. The system design process is another process that follows an iterative feedback loop. So beginning from where we left off before, you have already, let's say you've already got your requirement specifications. You've interfaced with your customer, you've done the needs assessment, and you've come up with your requirement specifications. These things, you can hang numbers on them. You can tell the customer, you've worked with the customer to say, this product is going to do exactly this. Okay, so once you have those requirement specifications, which tell you what it should be doing, you need to figure out how it's going to do it. And so that is this iterative process where you will develop concepts, analyze those concepts. So take your engineering knowledge, see if you can crunch some numbers, figure out what works. Then based on that, those numbers, right, you can synthesize a solution. If the solution doesn't quite work, go back to the analysis. And all along the way, anytime that you come up with a process or a solution or a subcomponent that doesn't work, just go ahead and reject that. All right, so follow this through this iterative process. And by doing this, you will go from a requirement specification that tells you what needs to happen with the overall system into a block diagram that describes how it's going to be implemented. So this process, right, you will conceptualize some solutions, synthesize the structure, analyze it using your engineering knowledge, refine it as needed, and then once you finish, document what your solution is going to be, use it in a block diagram so that you know how it works. All right, so conceptualization can occur via two sources, right? You could have external, right? So you could look at concepts that others have used to solve similar problems. So this is one way to start conceptualizing a problem. So when you have these requirement specs and you need to come up with a solution, you could start by looking at what other people have done, or you could try to find your own original concept. And the original concepts, those are more difficult and time consuming, although it might make a better solution in the end. In the synthesis stage, you will elaborate on the initial ideas in the form of a block diagram. Okay, and there are usually two conflicting forces in this stage, which one is the need for a quick design and one is the need for a novel design. So usually you are not able to make quick and novel designs. It's usually one or the other. So at this stage, you may need to come up against that harsh reality of needing to determine which solution is better, quick or novel. In the analysis stage, you'll determine if that synthesized system meets the performance and cost objectives, determine risk, estimate costs, and then analyze it from a systems perspective. So this, in the analysis stage, right, this is where you might need to, maybe break out your old textbook. Maybe you send some numbers to someone who can perform a simulation of the concept, but to get an idea of how exactly this will work. The synthesis analysis cycle is a refinement cycle of going from crunching those numbers and doing like that hard analysis on how it will work back into formulating a new way to solve the problem if things in the analysis point to it not being able to work. Okay. So each time you go through this cycle, right, your design will become more detailed and more of something that should be able to be implemented in reality. And the purpose of this, right, is to find major deficiencies or weaknesses or gaps that might exist between what you want to do and then what is possible or what is easily possible. In the block diagram, right, you want to be able to break the whole system down into the subcomponents. So the function of each block should be implementable with a single technology. So whatever the block is doing, so when you've broken down your pump into multiple subcomponents, each subcomponent block should have a single thing that it does. So using a single technology. So maybe one op amp, one FPGA, one microcontroller, something like this. It should be a single technology implements that block. Common functions should be grouped together into one block. So if you have maybe like a full wave rectifier or something, right, that is used multiple times, perhaps, group that into one block. So you have one full wave rectifier in your solution. Blocks are defined so as to simplify the interfaces between each other. So the interfaces, right, might be signals or power or data that's going through your system. So maybe one block gives data to the other block, and they should be simplified so that you can easily see how the blocks interact with each other. It's better to avoid having a feedback loop inside of the block diagram. That feedback loops are better to be their own block. Whenever you have these power or control or other signals that are going between blocks, you should indicate these. And then you should specify the characteristics or the parameters of whatever signals are going between the blocks. So if it's voltage, specify that it's voltage, current, power, etc. You should specify what it is that's going between the blocks. And then if necessary to, specify the timing or the sequence of how the block moves through. So the more complex your thing is, the more you might have to deal with the timing and sequencing. So as an engineer, you should take time to develop good and descriptive labels and text for these blocks and interconnecting signals. And usually these are going to be limited to just a few words. And if you need to have more information, right, that would be in notes or in an additional document or at the bottom of the page. The system specification document captures the design information for use in seeing the design through to a successful completion. And the purpose of that document, the documentation of your block diagram, provides the specifications for the total design and stores the details of the system engineering effort. So you'll have all of the details of how the subcomponents work. And you can also use this in a reference for the future design. So let's say in 5 years, you need to, I don't know, double the flow rate. Then you can go back to your original block diagram and look at each one of those subblocks and figure out, which ones could be kept, what needs to be changed, how it all would interface with each other. And that information is going to help you as well, right? When you go to test your full system, right, you will be able to do a better job testing if you understand how each subcomponent works. And then you can also use it in marketing, advertising, technical support might use that documentation as well. The system specification is organized into 5 sections. First, the concept explaining the principle of the operation, then a block diagram, then functional descriptions of each block, description of the system. So how do all those blocks work together in order to make the full system? And then a full detailed system analysis. So the results of the full system, how will the full system of all the sub blocks, how will it all work together in order to meet those requirement specifications, the thing that you hung the numbers on, the thing that you agreed with the customer on when you did that needs analysis. All right, so that is everything for this lecture. Thank you for listening, and I will see you in the next lecture.